A very good evening to everyone, and welcome to our online meeting. So I hope you can all hear me and everything's going fine. So the last meeting that we had, we did mostly video stuff. This is going to be a bit more talking and a bit of video as well. So Yeah, we'll see how it goes. Don't forget, you can ask your questions down in the little chat box, and um, I will probably look at them towards the end. So there you go. Um, we're going to kick off this meeting. We're not going to do the news this time because I'm actually going to be doing the news a bit more in depth. But yeah, let's have a look and see what is going on in the news. Let's go over here. And so the very first thing that we've got is a new image by Hubble, which has done quite an amazing thing. It's spotted a galaxy called NGC 2273. And it basically is a galaxy that has got a load of rings and spiral arms within spiral arms, which makes it quite unique. So if we have a look at this image here, this is of NGC 2273. If you have a look where that arrow is, you can see there's a nice ring all the way around. That is quite a easy one to spot. Those rings also appear over there. It might be a bit harder to see, especially if you're on a smaller device, but there you go. So at first glance, it looks like a simple spiral galaxy with two pinwheel arms like we used to. But you see that there are also these rings within the spiral arms and spirals within spirals. And this kind of galaxy we call a multi-ring structure. As this description suggests, it means that it hosts inner rings and actually two outer rings. So having all of that's quite unusual for a galaxy, but this galaxy gets a bit more complicated than that. We've got another interesting thing, and that's the core, as you can see even in the picture, is extremely luminous. So we call it a Seyfert or Seyfert galaxy, which has this very interesting quasar. So basically it's a supermassive black hole in the middle, and it glows very, very brightly. In fact, the output of that particular supermassive black hole and the quasar glows more brightly than the entire Milky Way galaxy, if you had to put all that together. So that kind of gives you an idea of what we're looking at there. One of the other things that we have a look at is this energetic outflow from a distant quasar. So again, if you had a look at last week's talk, we had a look at exactly what a quasar is. It's basically what's going on in the center of this galaxy. So researchers using the Gemini North telescope in Mauna Kea have detected the most energetic wind from any quasar ever measured. And this quasar comes with a wonderful name called SDSSJ1352, and carries on. And it's about 60 billion light years from Earth, so a hell of a long way away from us. But what makes this quite interesting is that when they measured the wind that this quasar created, it's traveling at nearly 13% of the speed of light and carries enough energy to dramatically impact the star formation across that entire galaxy. So that's quite an amazing one. We actually have known about this quasar for quite some time, at least 15 years odd. But the guys at the Gemini Observatory have been using some quite amazing computer modeling to have a look at some of these old quasars. And basically they got a massive computer, did all the new modeling, and this is what they found. So one of the astronomers at Western University who led these Gemini observations said that while high velocity winds have previously been observed in quasars, These have been quite thin and wispy, carrying only a relatively small amount of mass. The outflow of these particular quasars sweeps along at quite a tremendous amount of mass at incredible speeds. So the wind is crazy powerful, and we don't know how the quasar can launch something so substantial. So as well as measuring the outflow, they're also able to infer this sort of the mass of this supermassive black hole that's powering this quasar. So this object you're looking at is about 8.6 billion times as massive as our sun. So that's about 2,000 times the mass of the black hole at the center of the Milky Way galaxy. And if for those who know Messier 87, that galaxy that's got a really well-known black hole in it, 50% more massive. 50% more massive than that one. So yeah, these things are pretty big. So all these results have been published in the Astrophysical Journal recently, and the quasars now hold the record for the most energetic quasar wind to date. And this after a study of about 13 different quasars. So yeah, that's quite impressive as far as quasars go. So there it is again. So basically they were quite surprised because, you know, having known about this quasar for quite a long time, it was only recently now that they've discovered exactly how big it is and how amazing it is. So what these quasar-driven winds do is they sweep the material from a galaxy that is needed to form stars. So in this case, because it's so massive and it's pushing all this material out of the galaxy, it's preventing star formation in that galaxy. So you find star formation is pretty low. So they studied this thing basically in various different wavelengths. Using near-infrared was actually the better one for them. And so now that they've done this and they've used this computer to find this, they're now wondering what other things that they can find using the same software, and then going back looking into all this old data that we've got. So let's have a quick look here at this video that I've got, which kind of details it a little bit more. Yeah, and there you have it, all about the quasars. Having a look at some other amazing things that they've discovered is they've discovered that the universe may not look the same in all directions after all. So this is quite an amazing thing, because one of the main assumptions when you are entering astronomy is that the universe appears to be the same in all directions, so isotropic. So a paper which has just come out with astronomy and astrophysics suggests that this might not be the case. So let me swap this over here. So an international team of researchers using Chandra X-ray Observatory has been studying a number of galaxy clusters. And what it is basically is when you get the Big Bang starts, bang, and everything is meant to expand out at exactly the same rate wherever you're looking in the known universe. However, following these new research that's happened, it appears that this is not exactly the case. So looking at X-ray observations and temperature of the gas that's throughout the galaxy, they've discovered that it should be equally bright all over in an isotropic universe. However, they found that clusters with the same properties, similar temperatures, sometimes appear less bright in what we would expect in one direction and then brighter in another direction. And this is quite a significant difference because it's around about 30% of difference in brightness. So these differences are not random, but they do have a clear pattern depending on the direction in which was observed in the sky. So if we have a look again at this image there we go. You can see there's 4 of them that we are looking at there. A2199 at the top, RXCJ at the right hand side at the top, A85 at the bottom, and A3667 at the bottom. You can see that they look very different from one another, and the brightness varies quite a lot as well. So that's a pretty interesting thing. So what happens is, if the universe is not isotropic or is anisotropic, what is actually causing this? And one of the reasons could be dark energy, that in some parts of the cosmos it is stronger than the other parts of the cosmos, so it's driving the speed a bit further than it would normally, or slowing things down maybe. It's also a possibility that some galaxy clusters are moving faster than expected because of the gravitational influence of other clusters as well. So that's quite an interesting thing that they'll look at. Here's another video detailing a little bit about what is going on there.
One of the fundamental ideas of cosmology is that everything looks the same in all directions if you look over large enough distances. A new study using data from NASA's Chandra X-ray Observatory and ESA's XMM Newton is challenging that basic notion. Astronomers using X-ray data from these orbiting observatories studied hundreds of galaxy clusters, the largest structures in the universe held together by gravity, and how the properties they display differ across the sky. The result challenges one underpinning of cosmology, that the universe is isotropic, meaning it is the same in all directions. Astronomers generally agree that after the Big Bang, the cosmos has continuously expanded like a baking loaf of raisin bread. As the bread bakes, the raisins, which represent cosmic objects like galaxies and galaxy clusters, all move away from one another, as the entire loaf, representing space, expands. With an even mix, the expansion should be uniform in all directions, as it should be with an isotropic universe. But these new results may not fit that picture. This latest test uses a powerful, novel, and independent technique that capitalizes on the relationship between the temperature of the hot gas pervading a galaxy cluster and the amount of X-rays it produces, known as the cluster's X-ray luminosity. The higher the temperature of the gas in a cluster, the higher the X-ray luminosity. Once scientists can measure the temperature of the cluster gas, they are able to estimate the X-ray luminosity. This method is independent of cosmological quantities, including the expansion speed of the universe. After doing this, the scientists then calculated luminosities using a different method that does depend on cosmological quantities, including the universe's expansion speed. The results gave the researchers apparent expansion speeds across the whole sky, revealing that the universe appears to be moving away from us faster in some directions than others. The outcome of this study has two potential cosmological explanations, either of which would have significant consequences. The first involves galaxy clusters moving together through space in a way not fully understood before. In the second, the universe is not isotropic, perhaps because dark energy is stronger in some parts of the universe than others. While other tests are needed to determine exactly what this study revealed, astronomers will continue to ask, and try to answer, some of the biggest questions in and about the universe.
Yeah, so there you go. It's been some quite amazing breakthroughs recently, even despite all the lockdown and things like that. So moving on to the next one, is we have a look at the TRAPPIST-1 system. Now, TRAPPIST-1 system is probably the most amazing system that we have discovered. So in 2017 is when they announced the TRAPPIST system. And it contains at least 7 rocky planets. And what was quite exciting was that 3 of those planets are found within the star's habitable zone. So this system has also had about 8 billion years to develop the chemistry for life, so things are looking pretty good. At the same time, these planets are orbiting a red dwarf star, and that's given some doubts that there could actually be an atmosphere or liquid water around these things that would last for very long. But according to some research by the new team of astronomers, all comes down to the composition of the debris disk and the planets that it formed from, and whether or not comets were around to distribute the water. So the team responsible for this has just recently published their findings in the monthly notices of the Royal Astronomical Society. In terms of how the solar system came to be, astronomers generally agree that it formed about 4.6 billion years ago from a whole nebula of gas and dust and volatiles. This theory has it that these elements coalesced in the center first, undergoing gravitational collapse to create the sun. Then over time, the rest of these materials formed the disks around the sun, which eventually accreted to form the planets. So if we have a look here at this picture, there's the TRAPPIST system. It's a little bit smaller than our system, but that's how that's formed. Pretty similar to the way ours formed. So there we go. Where are we? Oops, sorry. Get back there. So we're just going to have a look at the TRAPPIST ones again, having a look at our good friend Fraser Cain, and he's talking about the different TRAPPIST-1 planets here.
I've been doing this space news thing for almost 18 years now, so I'm on a lot of mailing lists for the media. And every few weeks there's a big press conference announced, and then the rumor mill begins, blows the news way out of proportion, and everyone's expectations are driven sky high. So when NASA queued up a press conference this week to make some announcement about extrasolar planets, I was excited, but realistic. I've been burned before. Well, here we are, right after the announcement, and let me tell you, this is gigantic news, one of the most exciting discoveries in the history of the search for planets orbiting other stars, and in the search for life. So here's the news. A team of astronomers have discovered an extrasolar planetary system where there are 7 Earth I've been doing this space news thing for almost 18 years now, so I'm on a lot of...
Sorry about that. Had a bit of technical issue there. We'll start that over again.
I've been doing this space news thing for almost 18 years now, so I'm on a lot of mailing lists for the media. And every few weeks there's a big press conference announced, and then the rumor mill begins, blows the news way out of proportion, and everyone's expectations are driven sky high. So when NASA queued up a press conference this week to make some announcement about extrasolar planets, I was excited, but realistic. I've been burned before. Well, here we are, right after the announcement, and let me tell you, this is gigantic news, one of the most exciting discoveries in the history of the search for planets orbiting other stars, and in the search for life. So here's the news. A team of astronomers have discovered an extrasolar planetary system where there are 7 Earth-sized worlds orbiting a red dwarf star. 7. Not only that, but this is the best part, 3 of those worlds are orbiting within the star's habitable zone, which means that there could be liquid water on the surface of 3 of these planets. Suddenly, the chances for finding life in the universe went way, way up. The star is known as Trappist 1, and astronomers have known that it's had planets for a couple of years now. In fact, the name Trappist is short for the Transiting Planets and Planetesimals Small Telescope, which is the telescope in La Silla, Chile, which discovered them in the first place. It's also the Belgian word for kind of beer, so I'm almost certain this overlap is intentional. Transiting should tell you what technique they're using. They use the telescope to watch the light coming from the star over a long period of time. As a planet, or in this case 7 planets, pass in front of the star from our perspective, the total light dims a tiny little bit. The group of astronomers working with Trappist 1 originally announced that they'd found planets around the star back in May 2016. The news on Wednesday is that they found an additional 4 planets and figured out that some of these are in the habitable zone. The main thing to remember is that this is a red dwarf star, not a main sequence star like our own sun. It only has about 8% the mass of the sun, which is right at the very lower limit of what's even possible for stellar fusion. Any smaller, and it wouldn't even be a star. It's about 500 million years old, which is relatively young for a star compared to our own sun's 4.5 billion years. Now that said, it uses its fuel so slowly that it'll remain in the main sequence for another 4.5 trillion years, long after the sun is dead and gone. So with this kind of feeble light, the 7 planets are huddled up close to their star. What kinds of worlds are we talking about? Well, they're pretty extreme. Astronomers designate extrasolar planets by letter, starting with B, from the closest to the most distant. First up, the 3 planets which are too close to the star to have liquid water. Trappist 1b is almost exactly the same size as the Earth and orbits the star every 1.5 days. Days! 1c is close to Earth-size too and orbits every 2.4 days. 1d is smaller, only 77% are planet size, and takes 4 days to orbit. Now, the planets we're most interested in start with 1e, the innermost of the habitable zone planets. It's only 91% the size of the Earth, so it's a little smaller than Venus, but it receives almost exactly the same amount of radiation from its star that we get here on Earth. It takes just over 6 days to orbit the star once. Trappist 1f comes next, the same size as the Earth, and it has about a 9-day orbit, getting about half as much starlight as Mars does. The outermost habitable zone planet is 1G. It's 13% bigger than Earth and takes 12.4 days to complete an orbit around the star. Compared to our solar system, it would be found orbiting somewhere between Mars and the asteroid belt. Probably pretty chilly. After that is 1H. It's 76% the size of Earth and takes 20 plus days to orbit the star. So it's well outside the habitable zone of the star, and any water on the surface would be frozen. Now that said, the astronomers think that the atmospheric composition makes a big difference, so maybe more of them could have liquid water, or less. Now I know your mind is buzzing right now. 3 Earth-sized worlds orbiting within the habitable zone of another star. There could be life there. Well, maybe, but probably not. There's a few reasons why this system isn't the greatest place to go searching for life. Now for starters, we have 3 planets in the habitable zone of our own solar system, Venus, Earth, and Mars. And as we know, just because liquid water can be present, that doesn't mean that it is present. On Venus, the atmospheric pressure makes the world like an oven, hot enough to melt lead. Atmosphere is the problem over on Mars too, where it's not thick enough to trap in the heat. Mars is a cold, dry desert. You wouldn't last more than a few moments on a surface without a proper spacesuit. Even though liquid water could exist, that doesn't mean that it does exist. And there's another problem, the star itself. Trappist-1 is a red dwarf star, and these have a reputation for being temperamental. Some can produce mega flares that would scour the life off a planet like Earth, especially considering how close they have to be for the liquid water to form. Seriously, compare the orbits of the planets at Trappist-1 compared to the moons of Jupiter. That's how close they are. Now that said, the astronomers studying Trappist-1 say that it's a very quiet star, so maybe there's some good news there? Because the planets are located so close to their parent star, they're probably tidally locked, like the moon is locked to the Earth. This means they only show one face to the star. One hemisphere of the planet is in constant sunlight, while the other hemisphere is in permanent darkness. I don't know about you, but it sounds like it would make life harder. There is one idea that will fire your imagination, though. These planets are huddled so close together in the system that they're easy to see from each other. If you could stand on the surface of one world, the other planets would be visible in the sky. Not as points of light, but as actual worlds larger than the moon. One last thing to remember, this star is located 39 light years away. Now it's relatively close in galactic terms, but it's incredibly far away considering how tough it is to get to Mars. We have no way to travel there and study it any closer. Even messages to and from any intelligent civilization would take a single human lifetime to hear a reply. We're really only going to be able to observe these worlds from afar. This week was historic in the search for extrasolar planets. We still haven't found that elusive 2.0 yet, Earth-sized world orbiting a sun-like star in the habitable zone, but it's a collection of planets like nothing else we've ever seen. Once the James Webb Space Telescope and other big observatories get working, they'll tell us even more about their orbits, atmospheres, and even if they have exomoons. We'll get a much better sense of what star systems look like across the Milky Way and where we should be looking next. This episode was a bit of an experiment. We dropped everything to help you understand a big piece of news that broke this week. Do you want more of this? Let me know your thoughts in the comments. The search for another Earth goes on. Here's a video where I talk about what it's going to take to find a true Earth 2.0.
Yeah, so that's Fraser Cain passing on his wisdom there. I quite like old Fraser. He really boils things down to a really simple sort of level. So one of the things coming up this week is that the Trappist system they've discovered has got its own type of Kuiper belt. So there on the outskirts of their solar system is a whole big ring of volatiles and water and ice all sort of spinning around. So this is where all the comets and that come from, so water-rich reservoirs, if you'd like to call it that. However, you need to have quite a lot of these pounding the planets over a very long time to get any appreciable water there. So it is still quite interesting, this whole Trappist system. I think once the James Webb goes up and we can actually discover a little bit more about it, we'll actually hopefully get a little bit more information about that. So there's a question there saying, why do they start the planet designations at B instead of A? Because A is usually the star. So anything else after that is B, C, D. You'll notice also that they're not necessarily in order because they name them according to how you discover them. So that's quite an interesting one there as well. So moving on, a little bit. We're going to have a look a little bit closer at brown dwarfs. Because quite an amazing thing this week is astronomers have managed to measure the wind speed of a brown dwarf. So they've used the Koljansky Very Large Array and the Spitzer telescope, combine them to take measurements on certain brown dwarfs, and then they also compare it to things like Jupiter and Saturn, because of course they very, very close to a brown dwarf. Brown dwarfs, of course, are the most common sort of star, if you would call it a failed star, in our galaxies. So it's quite good that we try to understand these things. What they've done is they've studied a particular brown dwarf called 2MASS J104, blah, 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 blah. I'm not going to go through the whole thing. It's an object a little bit bigger than Jupiter, and it's about 40 times more massive. And it sits at about 34 light years out from Earth. So basically they are planets that are not massive enough to cause a thermonuclear reaction at their core, and that's the thing that powers a star. So they sit there on that kind of borderline between the two. So in this case, how they managed to discover these wind speeds is they have a look at the radio emissions that are caused by electrons which interact with the planet's magnetic field. And that is all rooted quite deep within the interior and then going around the outside, like this picture here. While the infrared emission comes from the top of the atmosphere. So it's looking at both of them. The atmosphere is rotating more quickly than the interior of the planet, and the corresponding difference in velocity is due to the atmospheric winds. So a bit of clever maths there, and you can then discover that how fast this wind is traveling. So they've calculated that the brown dwarf's atmosphere is rotating faster than its interior with a calculated wind speed of 1,425 miles per hour. I'm not sure what that is in kilometers per hour, but you can have a look at what that is. So Jupiter's wind speed you're looking at is about 230 miles per hour. So it's going quite a lot faster than that. So this technique can only be used to measure winds not only on other brown dwarfs, but also on any of the gaseous extrasolar planets. So yeah, it's quite an interesting new methodology that we can have a look at with distant planets. So let's have a quick look at another little video here. Oops, sorry. Okay, a bit of a technical problem there, but there we go. You can have a look there. There's Jupiter with the brown dwarf next to it. And you can see the magnetic field and the atmosphere at the top. You can see the radiation. You can detect it with the infrared. And you can work out the wind speed. In this case, I got it down to 650 meters per second. And then the interior rotation, that can work out the period is 1.758 hours. So pretty interesting there. Unfortunately, I can't get the video to work on that one, but yeah, quite an interesting thing. So moving on a little bit closer to home now, we found new images of the sun reveal these thin threads of million-degree plasma, which is quite amazing. So if we have a look at the image there, we've got the sun, and so when you expand it out, you can see all those little filaments that are there. So these are taken off very high resolution images using NASA's high resolution coronal imager, and you can see these amazing filaments sort of moving along the surface of the sun. So if we look at the next one there, we can actually have a look. There's the filaments on the left hand side, and then sort of a closer up version, you can see there it is with the size of the Earth. So you're looking at probably about a quarter of the size of the Earth or so, with some of them a little bit smaller than that. But it just gives you an idea of how really massive the sun is. So the HCAS, that's the high resolution coronal imager, is not aboard a spacecraft. Instead, it's briefly carried aloft by a suborbital rocket. Once it's in the air, the telescope is capable of zooming in on these solar features that are just 70 kilometers across. So that's about 0.01% the width of the entire sun. So that's a pretty awesome image taken pretty much from Earth. Until now, solar astronomers have effectively been viewing our closest star in standard definition, whereas the exceptional quality provided by the HCAS telescope gives you basically a UHD version. There was Robert Welsh from the Institute that led the team that said that. Think of it like this: if you're watching a football match on television, standard definition, the football pitch looks green and uniform. If you watch the same game in Ultra HD, then you start seeing every individual blades of grass excuse me, that jump up. And it's quite interesting. Researchers are not sure yet what generates these fine magnetic lines and these delicate threads. But they keep on looking, and hopefully we'll sort of understand this a little bit better in the future. Moving a little bit closer to home, we have detected our 100th lunar asteroid collision. So we've had two telescopes that actually look at this. So this is asteroids which collide with the moon. Now, this is quite an interesting thing, because a couple of amateurs have actually seen this happen. What happens is you look at the moon with a reasonably good telescope. When these asteroids collide with the moon, they collide quite energetically and actually produce a light flash. And you can actually pick that up. So we've got these telescopes which constantly actually look at the moon specifically for that. So you wonder why they're doing that. It's well, the Earth is constantly bombarded by all these bits and pieces, fragments of comets, asteroids, and that, but mostly they burn up in our atmosphere. And a few, particularly the larger that are a few meters, are potentially dangerous, but their numbers are not well known. We only discover them when they're relatively close. So instead, we have a look at the moon, and we see, because the moon's atmosphere is pretty negligible, even the little tiny asteroids that are traveling pretty fast leave quite an impact. You can see that by just looking at the craters. So when the little small asteroids and that strike the lunar surfaces at high speed, they can generate a flash of light. Scientists can then use that brightness of the flash to estimate the size and mass of the object which caused it, and improve our understanding of how similar objects are colliding with Earth. So typically these little asteroids weigh less than 100 grams and measure less than 5 centimeters across, and they are big enough to create these observable lunar flashes. It's quite interesting. I was actually involved with a project some years ago using amateur radio, where we were looking at detecting these flashes as they also release electromagnetic radiation. So we were looking at trying to do it that way. Unfortunately, it didn't quite work out like that, but the theory was there. So I was quite excited to actually see this back in the news again. So if we go back to the picture, we have a look where the little circle is. That's the 100th one that's been picked up. So the one that picked it up initially was one called the Near Earth Object Lunar Impacts and Optical Transients Project, or NELIOTA. They look for flashes which are easiest to observe on the dark side of the moon, so where it's not illuminated by the sun. So this is funded by ESA and operated by the National Observatory of Athens in Greece. It uses a 1.2 meter telescope and a twin camera system that splits the light of the lunar flashes into two colors. This helps the scientists to estimate another important feature of the impact, and that's the temperature of the impact. So since that project began, they've done about 149 hours of lunar monitoring, and they've detected 102 lunar flashes. What's impressive with the 100th detection is that it's the first time it's detected by two observatories. So using a 35 centimeter telescope, a new team at the Sharjah Lunar Impact Observatory, or SLIO, in the United Arab Emirates, detected a flash on 1st March 2020, and it was confirmed that this was the same event from the 100th NELIOTA detection. So what they've said is cross detections like this are pretty useful as they rule out the possibility of a slow, bright satellite being misidentified as an impact flash. So as we're building more and more of these observatories focused particularly on the moon, we're going to discover more and more about the objects that are circling around that are hitting us here on Earth. So yeah, definitely worth following up on that one. So moving on to the next one over here, we've got, sorry, there we are. An Earth-size habitable zone planet has been found looking at the old NASA Kepler data. So as you know, the Kepler Space Telescope was decommissioned in 2018, and there's been a huge amount of data collected. Now, what's interesting is they've been going through the old observations from Kepler 1649c. That's sort of the planets that they've discovered. Previous searches of using a computer algorithm had misidentified it, and basically researchers had a second look at a lot of the signatures and recognized it as a planet. And out of all of the planets found by Kepler, this world, which is located about 300 light years from Earth, is most similar to Earth in size and in estimated temperature. So could this one be the Earth 2.0? And much like the old Trappist ones, we'll probably find out in quite a ways in the future. So this new world is about 1.06 times larger than our own planet, and it receives about 75% of the amount of light that the Earth receives from the sun. So meaning that the temperature is probably going to be very similar to what it's like here on Earth. Unlike Earth, it orbits a red dwarf. None of these have been observed in the system. This type of stars known for stellar flare-ups, which could cause any problems with life taking place. there's a lot that's not known still about this. Current calculations on the planet size have significant margins of error, as do all of values in astronomy. And but it's a really, really good one to look at. Other close ones being, of course, Trappist and T-Garden is the other one. But what they've discovered basically is by looking at a lot of this old data from Kepler, there's still a lot to be found there. So for at least a good few years in the future, we will still be finding things thanks to Kepler. If you have a look at this image here, we can see that it's about the same size as Earth, which will make things quite interesting if we ever get there to take a look. So last on our list today is the NASA's Curiosity rover, and it's much like all of us. They've managed to work from home. So during this whole time of social distancing, they've been using video conferences and emails, and of course they can also operate the rover and conduct experiments all from their home. There's actually 4 members of the team working from their home with the rover right there. So quite interesting. They've already, while working from home, they instructed Curiosity to drill for a rock sample at a location which they called Edinburgh, and so they started doing that. They rely quite a lot on 3D imaging from Mars, and they usually study this with like special goggles. You can actually see. No, you can't really see it. But yeah, they have a look at things in 3D and then know kind of where to drill down. Typically, the team leaders decide where to drive Curiosity and how to do all the science. So working apart, they kind of do that already because there are quite a number of them involved. There's about 20 or so people involved, and they don't often all sit in the same room. So they do share screens and images and data when they sort of working anyway. So it wasn't too much of a hassle for them to work from home. But I thought, yeah, that's quite interesting how we can look at a rover all the way on the other side of the world, sorry, other side of the solar system, and follow what it's doing there. So it's quite an exciting time for all of us, including people working on rovers. So Ben says 100-gram mass, quite incredible how it creates a visible flash. What kind of crater or visual evidence would it leave? I'm assuming quite a small little crater. If you have a look at some of the imaging, you can actually see sort of where these things happen. So that's it, I think, for the meeting as such today. If there are any other questions, if you just pop it into the thing there. Don't forget, there are still 2 competitions running. There's the 2020 Great Barrier Astrophotography Contest. It's going to be photos taken from Great Barrier, which is going to be quite difficult to get to in the current circumstances, but some people might have some historical photos that they might want to submit. First prize for that one is, let me pop it over here, is $2,500, $1,300 second prize, $1,000 third prize, and there's another $500 prize. So that one is pretty good. We've got the 2020 New Zealand astrophotography competition. This is sort of run by Australian Sky and Telescope, Auckland Astronomical Society, our good friends at Astrons, and a whole bunch of other people. All different categories. So, if you're interested in that one, actually now's the perfect time for that. Get your cameras out and go and have a look at that. So I'm going to try and get the stellarium running. If I can get that running okay, then we will have a quick look at what is going on with stellarium and the stars that we can see currently. So there we go. Get a look around. So if you go outside now, head off to the west, you'll be able to see Rigel, Betelgeuse, Sirius, Procyon, Pollux all up there and running. Let me try and get all the other bits and pieces. Deep sky objects, let's get that up there. Planets. There we go. That's a bit better. So the west is where it's all happening at the moment. There's Orion with Rigel, Betelgeuse, and of course the thing to look there is the Orion Nebula and this part over here. There we go, Great Nebula of Orion. That's a good one to have a look at. You can actually see that with your binoculars. Of course, this all depends on whether it's cloudy or not outside. That's always a bit of a problem. If we sort of carry on sort of a bit more further up, got Sirius right up at the top over here. And there's Canis Major, quite a few nebula to be seen there. We pop over to the other side, there we go, and so we're now sitting in just off to the southeast. If we follow up the Milky Way here, we get up to Southern Cross up there, and of course over here, if we have a look over here, there's Omega Centauri, another really good one to have a look at with binoculars. Remember, you can actually see this through the naked eye as well if you've got really good eyes and it's a really dark sky. It's quite a big object, about the size of the full moon. Of course, not as bright, but there you go. So up in the top right hand corner, you can see there is the Southern Cross. Give you an idea of where to look in the night sky. Have a look just above. There's the Pearl cluster up there. There you go, running Chicken Nebula, a really good one to see through the telescope. One of the good things with your binoculars is if you just follow very slowly all the way up the Milky Way, there are just so many of the little nebula that you can see and little star constellations that you just don't normally see. There's a whole bunch of things that we just never really get to see with our normal telescopes even. That's why personally I prefer going out with the binoculars to take the general look, and then combining that with the telescopes, I can look really specifically at certain things. So if we head around towards the north, up at the top, the Beehive cluster, the top left-hand corner, just above Pollux and Procyon. Let me zoom out a little bit more there. If we move around here to the east, there's Virgo, with a potential meteor shower coming up there within Virgo itself. So keep an eye out for that. There's actually a few meteor showers happening over the next little while, so keep your eye out, keep on the Facebook pages, and you'll be able to sort of find that dates and things like that there. Of course, if we move over to the south over here, we've got the Small Magellanic Cloud, 47 Tucanae. There we go, 47 Tucanae there. The Small Magellanic Cloud up there. And then there's the Great Magellanic Cloud as well, which I haven't got on here at the moment, but all in the same area. So another one to have a good look at there if you have got the clear skies for that. So there we go. So thanks a lot for coming along and joining us. There Ben is asking about the celestial North Pole. Sure, that's quite a difficult one to show on here because we don't have a reference like in the northern hemisphere. So that will be somewhere up in this region over there. If you turn it around. In fact, over here, equatorial grid, there we go. So that shows where it is. So you can see the Magellanic Cloud, 47 Tucanae to the bottom right, and then it's a bit up from there. So there we go. Well, thanks a lot, everyone, for coming along. It was really great to see you all. Stay tuned, and we will let you know what is happening in future meetings. And I wish you all a very good night and clear skies.